Hey everybody, today I will be doing another video, and today I will be doing the hexadecimal to binary conversion, right? So last time we did binary to hexadecimal. Today we will do hexadecimal to binary, right? And there's a couple of things that we can actually take into account here. This is not really hard. It's not. It just requires a little bit of technique to identify these numbers, because remember that last time when we did to get the hexadecimal, we had to actually do 4 bits. We had to do 4 bits for each number that we got. For example, this one, we had to get 4 bits, right? For each. Well, that's why when I look at these problems, for example, part A, I'm not gonna say that this is 10. No. It is 1, 0, 8. A, letter A, 4, right? Now, the reason being is because I know that 10 in hexadecimal, we don't say a 10, we say A, and 0, we say 0, right? So but like I say, I will not try to refer to this table too much, because I want to make it sure that you understand how to break these problems into pieces, into blocks, identify them, break it into blocks, and then go from there, right? And when I say break it into blocks, remember, we're thinking about base 2 here. So the bottom line is I have to use the base 2 to get to the middle ground, how we got these numbers in the first place, right? So now what I'm going to do, I'm going to use the number system to convert these numbers into decimal first, right? Not exactly to get the sum of the numbers, but each individual number, right? So each individual number, that's what I'm trying to say here. Not the sum, but each individual number I see here, that I see in this problem, I need to kind of convert that to decimal and then go from there. Because if you look from 0 to 9 in hex, it's the same thing in decimal from 0 to 9, right? The only one that changes is from 10 to 15, right? So that's why I need to kind of make it look like the decimal number, so I can actually start, working these problems out, right? So let's start with part A, right? So part A, what I will do is separate the digit of each number that I have. So I will put number 4, right? I will put number A is, and so the another thing would be, how do I know what is A? Let's say that you don't have this table, because sometimes probably the teacher is going to say, okay, don't use the table, or just try to do it without using any type of table, any type of reference. Well, it's a good thing to remember that from 0 to 9 is just basic 0 to 9, right? It's just simple. It's the same in the decimal counting system. It's the same. The only thing that is different here is after, starting at from 10. So we know that A is equal to 10, B is equal to 11, C is equal to 12, and D equal to 13, E equal to 14, and F is equal to 15, right? Okay? So if you remember this, it's easy to remember from 0 to 9, which is the same thing, right? Okay, because we want to get this number, whatever we have here, in this case the A, we want to make sure that we have it in this number, so we actually can go from this numbers to binary, right? Like I said, I want to get to kind of look this number to look like decimals, so I can actually go back to binary. Okay. Okay, so how? Okay, so I get 4 now, and then I get 8, which is what? This is 10, right? And then I got 0, well, 0, right? And then I got 1, that is 1, right? So now I have these numbers here separated, right? So I need some space to work them out, right? Because now I am thinking about base 2, right? Why I'm thinking about base 2? Why I'm thinking base 2 now? Because I am thinking about how do I get these hexadecimal numbers to actually, let me explain something here. Remember that we using this technique just to represent the numbers. But in hexadecimal, and let me make this myself clear again. In hexadecimal, when we say a number like this one, we're talking about 4 bits. 4 bits. Okay? And because it's easy to get confused. It's very easy to get confused and saying, okay, that get confused between decimal and hexadecimal. Okay, now, because they look the same. If you look here, this look like 10, but it's not 10, right? So, this is represented by 4-bit. This also was represented by 4-bit when they got this, right? Now, okay, so let's start. So I have to think about like this, and I will do this just I will do everything that is required to in this first problem. I'm not gonna do it in part B and part C, but I will do it in part A, how we actually do the base 2 type, right? Okay, so here we said 2 to the 0 power, 2 to the 1 power, 2 to the 2nd power, 2 to the 3rd power, right? So this is what? This is 1, 2, 4, 8. Here we got, that's for the 4, right? Let's do for the 10. So 2 to the 0 power, 2 to the 1 power, 2 to the 2nd power, 2 to the 3rd power. Again, we get what? We get 1. We get, making sure that you kind of put them separate a little bit. That way you're talking about bits, you don't want to put like some number, like if you put 2 and 1 close, it look like 21. So that is 1. Actually, that is 1. That is 2. That is 4. That is 8. Right? So So, all right, now, these numbers here, this number here, right? So now let's do the zero. Well, the zero is just simply all of them are zero, right? I don't even have to do this math. Alright, so I can just put 0, 0. Alright, so you know what? Just put, because technically this is 4 zeros, so let's put a 4 0 right here for this one, right? 0, 0, 0, 0, right? Because we're going to need those zeros anyway. Here I put 2, I put 1. You know what? Alright, so think about what we did last time. What we did last time was that 1 times 2 to the 0 power, right? That number is 1. 1 times 1 is equal to 1, right? So that's how we got all these numbers. Now we're thinking about the same thing here. But when we got a 0, that means everything has been multiplied by 0, which make the number 0 right there, right? So we just drop that 4 zeros down, and then we do the same. We do the same thing here. In this case, we don't have to do it because we know there's 4 zeros. Just bring the 4 zeros there. But here I will do 2 to the 0 power 2. Let me just do a little bigger too, because that doesn't look like the camera is going to kind of. Okay, so that is 2 to the 1 power, 2 to the second power, 2 to the third power, right? Right, so here we got what? We got 1, 2, 4, 8. And again, I am just doing this in this problem. And the next two parts are not going to do this, right? Okay, now that we have this separate, all the numbers, we can actually see what numbers we need to complete the decimal part, right? Because that's what we're doing. We're going from hexadecimal to, we're doing from hexadecimal to binary. So the next step is what numbers or what bits I need on or off, or zeros or one, like whatever whatever way you want to think about it, and whatever way is helpful for you. If you want to turn the bit on and off, or you want to say zeros or one, right? Technically, basically the same thing, right? When the computer said off, that means that email has not been sent, right? You cancel it or whatever, right? If you send an email, then that means there is a 1 in there, right? Same thing, right? So let's do this. How do I get 4? Well, I get 4 by turning this bit on, the 4 on, right? So that means that this is going to be off, on, off, right? How do I get 10? Right? So remember when we went from binary to hex, we had to add the numbers in the block, right? So how we get this hexadecimal to be 10 then? Well, was 8 and 2, right? So that means this is off and this is off. So it's 1, 0, 1, 0. And actually can go back here and look at 10. It's 1, 0, 1, 0, right? So this 0, just bring them down. 0, 0, 0, 0. And how do you get 1 here, right? How do we get this one? Well, just by turning what bit on or off? Well, right here. This is the only one that needs to be on. So we say that is 1, 0, 0, 0, right? And the answer for this, usually the books only write, you have a bunch of zeros here, they don't bother in writing these 4 zeros to the left. They just start from the first number here, which in this case is going to be 1 to the right. So technically the number 10A for base 16 is equivalent to is equivalent to 1, 0, 0, 0, 0, 1, 1, 0, 1, 0, 1, no, 0, 1, 0, 0. Alright? So that will be the and base 2. That will be the answer for part A, right? Now let's do part B real quick. Alright, let's do part B. Okay, so part B, I have C, F, 8E, right? So here, what is E? E, we say that was 14, right? It's 14. So I put 14, and I put 8, and I put 15, right? I put 15 because for the F, right? And I put 12 for C, right? 12 for C, right there. Now, let's start working this thing now. Working it out, right? Let's start with 14. How do I get 14? It's again 1, 2, 4, 8. That's for the 14. And I do 1, 2, 4, 8. That's for the 8. And I do 1, 2, 4, 8. That's for the 15. And I do 1, 2, 4, 8. That is for the 12. Let's start with, and remember these are that is divided by 4 bits. Right? Okay, so now that I have this separated like that, how do I get 14 here, right? Well, I get 14 by adding 8 plus 4 plus 2, right? So that means that this need to be on, this need to be on, this need to be on, this need to be off, right? That is for 14. How do I get 8 here? Well, just, it's right there, just 8 is right there. This 4, 2, and 1 need to be off, so 1, 0, 0, 0, right? How do I get 15 here? Well, 8 plus 4 plus 2 is 14 plus 1 is 15, so they need to be on. So that's why it's 1, 1, 1, right? What about here? How do I get 12? Well, 12 is just basically 8 plus 4. So this needs to be on, this needs to be on, this needs to be off, this needs to be off, right? So now I need to put this together, right? I need to make one number because now we're talking about one number, right? And so you're talking about one number. So the binary, I'm sorry, the binary representation for F is going to be this number. For part B, for part B, which is going to be C, F, 8, E, is represented by the number 1, 1, 0, 0, 1, 1, 1, 1, 1, 0, 0, 0, 1, 1, 1, 0. Right? And that is base 2. Right? So that is part B. Alright, so that's part B, right? So let's do part C. Okay, so part C. Part C, right? So part C, I got what? I got 9, 7, 4, 2, right? So I write 2 there. I write 4 here. I write 7 here. And I write 9 here, right? So how do I get this, right? So basically the same thing, just start doing the same exact thing. So 1, let me just do it here so I get a little more space. 1, 2, 4, 8, that's for the 2. 1, 2, 4, 8. And that's for the 4. Alright, that for the 4, and this for the 7 is going to be 1, 2, 4, 8. That for the 7, and 1, 2, 4, 8. That for the 9. And again, now we just kind of identify the 4 bits. Just kind of identify the blocks. Okay. Now that we have this, we actually see what numbers, what bit need to be turned on or what bit need to be turned off in order to get these numbers, right? So how do I get 2? I get 2 by turning just one bit out of this, right? Because if I add any of its numbers, it's not going to equal 2. So I put 0, 0, 1 because I need that bit on for the 2, and I'd say 0 on this one, right? So that is 2. Let's do 4. How do I get 4? Well, just by turning this bit on, right? So I said, 0, 1, 0, 0. That's 4. And again, you can actually cross-reference into the table. 4 is equal to 0, 1, 0, 0. Right? So let's do 7. Well, how do I get 7? By turning this 3 bits on. 4 plus 2 plus 1, 4, 6, 7, right? And again, this is 4 plus 2 is 6 plus 1 is 7, right? That's how we think, right? In this process. So we say that 1, 1, 1, 1, and that is 7. And again, that is a representation for number 7. Okay, so let's do the last one here. So how do I get 9, right? So a plus 1 is 9, right? So I put 1, 0, 0, 1. And that is the binary representation for that number. So the binary representation for 9, 7, 4, 2, base 16 is 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 0, 0, 0, 0, 1, 0. And that is base 2. Okay, so that is the representation of that number in hexadecimal, and that is the representation in binary, right? So this has been the lecture for today, and I hope you learned something. I hope you learned something in this lecture. Of at least you know how to convert, how to go from hexadecimal to binary. Thank you for watching.